So now that we have seen both the formal definition and the computation definition for matrix multiplication, we are ready to explore some of the standard properties of matrix multiplication. So these are going to be important to not only computation, but to theory as well. So here, we are going to let A be an m by n matrix. And we also want to go ahead and let B and C be size-appropriate matrices. Now, when we say size-appropriate, what we mean is that matrix B and matrix C are going to be of a size such that the following properties are going to be defined. Because we know that the number of columns of the first matrix must be equal to the number of rows of the second matrix for multiplication to exist. We also know that two or more matrices need to be the same size for the sum to exist. So, here we go. Our first property is the associative law of matrix multiplication. And this property says that if we have matrix A multiplied by the product of matrix B with matrix C, that this is the same thing as taking the product of matrix A with matrix B and then multiplying by matrix C. So the order in which we multiply these matrices does not matter as long as they are size appropriate. Now, with the second property, we have the left-hand distributive law. So the left-hand distributive law says that if we have a matrix A multiplied by the sum of matrix B with matrix C, that this is equivalent to the product of matrix A with matrix B plus the product of matrix A with matrix C. Now, I want you to note that when we have the matrix on the left-hand side, as we do in this case, here we say that we are left-hand multiplying by matrix A. So we are left-hand multiplying by matrix A. Now, with the third property, we have the right-hand distributive law. And the right-hand distributive law says that if we have the sum of matrix B with matrix C, and then we multiply this sum by matrix A, that this is equivalent to the product of matrix B times matrix A plus the product of matrix C times matrix A. Now notice here how the side has changed. How in this case we have matrix A on the right-hand side. So here we'd say that we are right-hand multiplying by matrix A. So it's important to note, are you multiplying on the left-hand side or are you multiplying on the right-hand side? And it's important to note the difference because as we've seen already, matrix multiplication is not necessarily commutative. So you're not necessarily going to get the same answer if you multiply on the left as when you multiply on the right. The next property that we need to explore is the property of scalar multiples. So this property tells us that if we have a scalar, say little c, multiplied by the product of matrix A times matrix B, that this is equivalent to taking the scalar multiple of matrix A first and then multiplying by matrix B, which is the same thing as taking matrix A and multiplying it by the scalar multiple C times matrix B. And this is for all scalars C. And last but not least, we have the identity for matrix multiplication. Now this identity says that if we have the m by m identity matrix multiplied by matrix A, this is equal to matrix A, which is also equal to matrix A multiplied by the n by n identity matrix. And this makes sense because the size of your matrices is so important to matrix multiplication. So if we think about the left-hand side first, we know that I sub m is the M by M identity matrix, and we know that A is an M by N identity matrix. So we can see here that the number of columns of the first matrix equals the number of rows of the second matrix, implying that this product I sub M times matrix A exists. Woohoo! Versus if we think about the right-hand side of this product, here we have matrix A, which of course we know is an M by N matrix, and we have I sub N, which we know is the N by N identity matrix. So in this case, again, we can see that the number of columns of the first matrix matches the number of rows of the second matrix, indicating to us that the product matrix A times the N by N identity matrix also exists. Woohoo! So these are the standard properties for matrix multiplication. Again, they are going to be important to both computation as well as theory. Now, before we go ahead and start looking at examples, we need to make note of some important differences between our good old friend regular algebra and matrix algebra. So here we are looking at some of the general cautions for matrix multiplication and matrix algebra. So I want you to note as we get started that the following statements are generalizations. So in some cases, these may hold true, but in general, the following will not hold true. So in other words, we need to be mindful of the differences between regular algebra and matrix algebra. Now, this first case we've already explored together, and this is that matrix multiplication is not commutative. So we can say that in general, matrix A multiplied by matrix B does not necessarily equal matrix B times matrix A. And we saw this with the last example. So in the last multiplication example, we saw that matrix AB was not equivalent to matrix BA. So we want to be mindful of this as we proceed. Now, I do want to make a little love note here that in some cases, in special cases, they are equal. So if we find that matrix or the product of matrix A with matrix B is equal to the product of matrix B with matrix A, then we say that matrix A and matrix B commute with each other. And again, we'll be exploring this case, this special case, in far more detail in the very next section. The second cautionary generalization I'd like to point out is that cancellation laws do not hold true for matrix multiplication. So again, we can say that in general, if we find that the product of matrix A with matrix B is equal to the product of matrix A with matrix C, we can't make any assumptions about B and C. So we say that then matrix B does not necessarily equal matrix C, which is different from what we know from algebra. So let's think about a quick example of this. So let's let matrix A be the zero matrix, and we'll do a 2 by 2 case. So matrix A is a 2 by 2 zero matrix. We have matrix B is a 2 by 2 matrix, 1, 2, 3, 4. And let's let matrix C be the matrix 3, 4, 5, 7. So we can see here that matrix A times matrix B is certainly going to be equal to the 0 vector, which is equivalent to matrix A times matrix C. But we can also see that matrix B certainly does not equal matrix C. So again, the cancellation laws do not necessarily hold true for matrix multiplication. So we want to be mindful of that. We can't make any assumptions. And last but not least, if a matrix defined as the product of matrix A with matrix B is the zero matrix, then we cannot conclude that matrix A nor matrix B are the zero matrix. So what is this saying? Well, this is saying, in general, that if the product of a matrix A with a matrix B is equal to the zero matrix, then matrix A does not necessarily equal the zero matrix, nor does matrix B not necessarily equal to the zero matrix. So we can't make any assumptions here. And again, let's explore this with a quick example. Let's let matrix A be the matrix 1, 0, 0, 0, and we'll let matrix B be the 2 by 2 matrix 0, 0, 0, 4. So they're both 2 by 2 matrices, so we know that their product exists. So we're taking matrix A, which is 1, 0, 0, 0, and we're multiplying this by matrix B, 0, 0, 0, 4. So let's see what happens when we apply the row-column rule. So we have the first row of A times the first column of B, so that's going to be 1 times 0 is 0, plus 0 times 0 is 0. We then have the first row of A times the second column of B, so 1 times 0 is 0, plus 0 times 4 is 0. Now we move to the second row of matrix A. So the second row of A times the first column of B is 0 times 0 is 0, plus 0 times 0 is 0. Then we have the second row of A multiplied by the second column of B. So 0 times 0 is 0, plus 0 times 4 is 0. And look at this, we're left here with the zero matrix. So we can see that even though matrix A times matrix B is equal to that zero matrix, neither matrix A nor matrix B are the zero matrix. So we can't make any assumptions. There are differences between regular algebra and matrix algebra. So we want to be mindful of these three generalizations as we proceed through computation.